Plasma cortisol. Yeah, we didn't do saliva. That might have been something in retrospect we might have done, but you can't do everything, I guess. Okay, with that, I think I'm going to ask Dan to come up. And we have a Belsky. I'll work on the screen thing at break.
So the story here is that I'm not able to put this into presentation mode.
I can't do that right now. I could try.
So if we just do that, it crashes. Oh, I see. So, but I think it's I think you can.
Let me try the mirroring thing.
If we I think we can fix that. So yeah, in displays.
Yeah.
Sorry, we were on a. Yeah.
Let's see what happens. Nope.
So what if we just try to drag this over there? So.
I'm sorry. No, wrong one.
It's that one. But I think. So I think we can. So you want to? I think he can. I think we could just. Here, let's try this.
Yeah. Yeah. Yeah.
It just doesn't work. Sorry? Mirror displays.
There were hotbox samples collected at baseline. You got those hotbox samples because they are arterialized blood. There are no remaining hotbox samples, period. So all this serum and plasma collected under non-hotbox conditions. These were at a different time, for example, in the protocol. Yes, it's a different visit.
We just have to go with it. Let's see what we can do for maximizing. Sorry for this version, I think we'll just make do. Well, I think we're not going to get it. I don't know what exactly is stored here, but that's fine. Yeah. Okay. So. Yeah. All right. So my apologies. I think most of this will probably be illegible to those of you in the back, but I'll talk and point, and those of you on laptops can log into the WebEx and see it in slightly higher resolution there. Okay, so I'm Dan. I'm here from Duke, and I'm going to give you an example, I guess, of what can be done with the calorie data, what I did with the calorie data. And I see a few familiar faces from the gerontology meeting in San Francisco, so apologies for some redundancy. There will be new data at the end, though. So I'm going to do my thank yous and acknowledgments at the beginning, so I don't run out of time here. I want to point out Bill, Carl, and Kim, who you've already met. Manju, I think, is in the back, who I have not met before in person, but has been tremendously helpful, and who I need to get a picture of so that I can put your face on this slide as well. And then Karen Abramson and David Corcoran at Duke, who helped generate these molecular data. of course, the U24 and then various other National Institute on Aging instruments that have supported this work. I'm going to try and do three things here. I'm going to introduce this idea of biological aging as a treatment target for health span extension that is sort of the foundation of this project. I'll talk about the paper we just published in the Journals of Gerontology with CALERIE data, and then I'll show you some work that really just came alive this past week with samples from the biorepository. Okay, so step one. You've all seen data like this, and for those of you in the back, this is a graph showing on the x-axis chronological age and on the y-axis burden of disease measured as disability-adjusted life years. This is actually an NIMH slide, so everybody's getting into the act of age-dependent increase in burden of disease. The point is there's a lot of lines here, each line representing a different family of chronic conditions affecting a different organ system in the body. They're all increasing with advancing age, many of them exponentially so. And it's from data like this, as well as molecular biology in animals, that has suggested a sort of revision of our general idea of aging from a summary of the bad things that happen to you when you get old to actually a molecular process that may be a root cause of the many diseases that afflict us as we age. And so there's, to some extent, a crystallization of understanding of some cellular level changes that begin to accumulate as we age that give rise to that increasing burden of disease from many different chronic conditions. A couple of prominent papers from the last few years down there at the bottom. But most importantly, when we think about these potential molecular routes to the process of aging, is the notion that it may be possible to slow down or reverse this accumulation of cellular level changes through what I've learned to call geroprotective interventions. And these geroprotective interventions can take a variety of different forms, from the pharmacologic to the behavioral. So this is my little caloric restriction image down there, but we'll get into that. Before we do, though, I want to talk about when we might think about intervening and why CALERIE is especially relevant for thinking about geroprotective intervention trials. As I was introduced to the field of aging, it was something that was pursued in studies of older adults, so people at the end of their lifespan who are developing disease, becoming frail and dying. Of course, there's also a beginning to this story as well, and for those of you who were at the meeting across the way in the last couple of days, I think you heard from Matt Gilman talking about how early exposures can structure risk for disease, disability, and death at the other end of the lifespan. So fetal programming, developmental origins of health and disease. But the idea is things happen to us at the beginning of life that change the way we age at the other end of life. And where we are now, I think, is a further elaboration of this model as we begin to connect these dots. In which we can think of this process of aging as linking the accumulation of exposures with the development of disease, disability, and death, and suggesting potentially a target for intervention. Okay, so here's basically the idea, is that we have exposures accumulating from early in life, affecting changes to physiology that precede the onset of disease, suggesting that preventive intervention might most productively begin relatively early in life. So here again is a curve showing you expected increase in morbidity across decade of life, and what we'd like to do is deliver some kind of geroprotective intervention relatively early on, which would shift that curve to the right, sort of rectangularize, as the demographers like to say, the morbidity curve. So I think this is a relatively straightforward idea, and we can imagine a relatively straightforward experiment in which we would test the potential geroprotective capacity of an intervention. And if we were dealing with something like a mouse, we would take a mouse and another mouse, and we give one of them a drug or a therapy, and we would follow them until they got sick, disabled, frail, died. And then we'd count the difference, and we'd call that the geroprotective effect. We can, of course, imagine the same experiment in humans. Now, we can do this experiment in mice over a series of months. In humans, that same experiment, if we imagine intervening in someone's 30s or 40s and then following them up to the onset of chronic disease or disability, it would take decades. So that's prohibitively expensive and time-consuming. We're not going to follow people for decades as a first test of the human effectiveness of a candidate geroprotective therapy. But it may be possible to run a slightly shorter trial if we can move from measuring actual health span to a proxy, a sort of a surrogate endpoint for health span extension, which would be a change in the rate of biological aging. And there are now a number of candidate methods to quantify this process of accelerated aging that we could imagine using as surrogate endpoints in these trials. Now, I realize we're a long way from the FDA definition of a surrogate endpoint here, but just bear with me. The idea is, as proof of concept, can we investigate whether a candidate geroprotective therapy alters a measured rate of biological aging using some of these methods that have been suggested. So in the context of this alternative geroprotective trial design, we would follow our treatment and controls for the same amount of time. And the question would be, does this rate of aging that we're observing in these individuals vary across treatment group, right? So if this is time during the intervention, and here's now the biological age of the individual, not their chronological age, which of course is increasing identically, we would expect a slower rate of increase in the treatment group as compared to the control group. So that's the model. Which brings me to an application. So wouldn't it be nice, if this is an idea we have, if we had a geroprotector that we were pretty sure worked, that we could try this out on? And as Bill explained, caloric restriction is essentially the oldest established geroprotective intervention on the books since at least the 1930s. We've known that it can make mice live a lot longer. We now have data that it can make monkeys live a lot longer. And as some of the data from CALERIE have shown, there are suggestive effects on human aging. Again, this is the website. That's the diagram. I won't belabor that point. Caloric restriction in CALERIE, as Bill noted, wasn't quite the 25% that was planned. But on average, the treatment